having seen the measurement of force, next measurement naturally is a torque. How torque is obtained? It is force acting over at a distance from an axis, that is a torque. Also moment also similar dimension, that is force times distance. So what is the difference between moment and torque? Moment is given by Newton meter, torque also given by Newton meter, but the difference between these two things is that when moment is acting over a body, if the body gets twisted about an axis, then the moment is called torque. So torque is again a moment, but it is under certain circumstances we call the moment as torque. Then the circumstance is when the moment twists the whole body about an axis, then moment is termed as torque. So the dimension is same as moment, that is force into distance. So that is now torque. Now torque is to be measured in engineering applications under two situations. Sometimes torque is the shaft is stationary, one end is fixed, the other end we apply a torque. Again the shaft get twisted about the axis of the shaft. Secondly, the shaft may be continuously rotating 1000 rpm, 5000 rpm or whatever it is, 10 or 20, it is continuously rotating, then also you are supposed to measure the torque. So now we will see the measurement of torque under two different situations, that is when the shaft is rotating, and second situation when the shaft is not rotating. And for the rotating shaft we have got two methods, principally two methods. First method is called absorption type of measurement. Here normally you would like to have the speed torque characteristic of a driving motor or an engine. In such situations, that is only engine or motor is there, and you want to find out the speed torque characteristic, as speed is increased or decreased, how the torque is varying. So that is a prime mover, that characteristics when you want to find out, then mostly you go for absorption type. Absorption type we have got few options, that is one Prony brake. These things are done in the undergraduate level for testing of IC engines, Prony brake, and then water brake, and eddy current dynamometer. So these are the devices normally used for absorption type of measurement. Prony brake essentially over for example IC engines output shaft, one drum is fixed and a number of blocks, wooden blocks are arranged, and then at the one end you will have the counterweight, and the other end you can have somewhat like this. Just suppose this is the drum, you will have the blocks, and all up and here. So at the end of the arm, these two things are fixed, and the end of the arm the weight is hung, and you have got a set of again blocks, these wooden blocks, and here you have the counterweight. Now this will be rotating in this direction, the wheel is rotating in this direction, and by hanging weights and noting down the distance, the torque is given. So it is held by, you have to tighten it with a number of screws. Here also you have to tighten it. So as you increase the tightening, then the grip of the wheel will be increased, and the set of wooden blocks will try to rotate along with the rotating drum, but that is being restrained by having a lever and hanging weights. So this moment is acting in this direction, so frictional torque in the other direction. Now you will find W into L will be the torque absorbed by the set of wooden blocks, and that multiplied by the RPM will give the power. So that's why sometimes power measuring instruments are called dynamometer, because torque multiplied with speed will give the power. Normally dynamometer should be used only for power measurement, but some of the torque measuring devices also this is made use of. So W into L will be the torque, this absorbs the whole power developed by the engine, hence it is called absorption type of measurement. In transmission type, no such absorption is made, the whole power is transmitted. So in this situation there is a motor, for example there is a motor that is coupled to a generator, for example this is generator and this is a motor. In such situations this is motor fixed, this also fixed, and what is the power transmitted to the generator? So the power source, and this is a power sink, or it may be a pump, motor to pump. So both of them are there. You normally you go for transmission type of measurement. So by one of the methods, we are going to learn 2-3 methods, that is transmission type of measurements. So in absorption type, all the energy is absorbed by this method. So when you absorb energy, then this whole thing is heated, and to cool it, normally in the drum we pour some water in the during experiments in IC engines. This is one of the experiments under undergraduate level. So otherwise we may have water break, the viscosity of water is made use of, and that is the second torque measurement, using water break. Third one is eddy current. Eddy current type of measurements. There you will have a disc rotated by the shaft. So this is rotating shaft, and here you will have the magnet, permanent magnet arranged, and the gap, this is north pole, this is south pole, this is a fixed one. This is rotating from the motor. From the motor, this aluminum disc, aluminum or copper disc also you can have. So for example, aluminum disc, it is rotated by changing the distance between the rotating disc and the permanent magnet. We introduce a different torque on it. That is, when a metal rotates in the vicinity of magnetic lines, eddy currents are produced, and that magnetic lines interacting with the coupling with the main magnetic lines, a torque is there opposing the rotation of the disc. So here also a little bit heated up, it is dissipated to the atmosphere. So by changing the gap, we can have different torques on it, and the whole torque is absorbed, and thereby we are measuring by measuring the gap, we can measure the torque applied on it. From some other calibration methods we can do it. So these are the 3 methods normally adopted for absorption type of measurement, but many instances we are asked to find out the torque transmitted by a shaft. So for example, motor to generator, and the first method what we are taking up is this is purely mechanical device, Eddy cyclic train transmission dynamometer. This is the device explained in Bevan, theorem emissions Bevan. Here when the motion is taken from motor to generator, such a gear system should be incorporated in this system. Then only, so for that is input shaft A is coupled to motor, and then the output gear, this input gear A is coupled to motor, and the output gear C is connected to generator. In between you should have this intermediate gear B. So this set of gears you can arrange it, and now when the torque is transmitted through this set of gears, the torque is measured automatically by putting different weights here against this reference mark. The principle of functioning is the torque T is acting over the gear A, which is fixed to the motor or the driving source, and that torque is realized as a force at the pitch line of the gear A. In such a way, T is equal to F into RA. RA is the radius of the gear A. And B is the intermediate gear mounted freely on the lever. This is a lever, gear B, I will write it, gear B is freely mounted on the lever, that is, it is supported on the lever, and the lever is freely mounted on the shaft of gear A. These are the construction details. The lever is mounted free on the shaft here. So, now when the gear A rotates, B will rotate in this direction, and B is driving the load on the gear C. So, the reaction of load will be in this direction. Gear C is rotating in this direction. So, reaction of C will be in the opposite direction. So, you will find 2F are there, and the reaction of these two forces will be taken up at the center support of the gear B, and so this is here you have got 2F is the force on the lever, since B is freely supported on the lever. So, now the lever is under a moment, that is 2F into A, because lever is mounted here. This is counterweight to balance the weight of it the other side of the pivot. This is more or less pivot of this lever mechanism, and the counter will be accounting for the mass of the lever in this direction. So, now the moment is 2F into A. 2F into A will be the moment about the pivot of the lever, and that is to be balanced by hanging weight W into L. By adding weight we can balance it so that it stands against the reference mark. So, now we find W is equal to 2FA divided by L. And now we know F is nothing but T, F is equal to T by RA. So, substitute for F, then you will find W is equal to 2, F is equal to T by RA into A by L. So, from here torque is equal to W RA into L by 2A. So, this is the torque, that is F into RA. You can also have F, correct. So, in this except W, RA, L and 2A are all known. So, it is 2L W into RA. Yeah. All the except W, all the parameters are known, and that means by having different weights for different torque, we are measuring the torque. This is the principle of measurement by epicyclic transmission dynamometer. That is what is shown here in the signal flow diagram. We have got a torque available that is converted into force F at the pitch line of the gear A. By using gear B and lever, we convert that force into a moment equal to 2F into A, that is being balanced by W into L, that is moment is converted in terms of W force by having the lever. So, as per this equation, now T will be W can be calibrated in terms of the weight, different weights can be calibrated in terms of torque. So, by adding different torques here, then you can find the total torque transmitted by this instrument. So, this is one method. Second method is reaction principle. Second method B, reaction principle. That is when the torque is developed. For example, we have got say a rotor, and that is mounted in a stator. So, this is rotor. So, this is stator assembly. We have the bearing here, bearing. So, rotor, and this is the stator of an electric motor. This is shaft. Now, when a torque is developed in a rotor, the basic principle behind this principle is, when a torque developed in the rotor, in the stator we will have the opposite, the reaction will be felt in the stator in the opposite direction. This is the principle, action and reaction. That is, the torque T is developed when torque T is developed in the rotor, the stator will realize the same torque, but it is in opposite direction. It is similar to when we use a gun, when the bullet moves forward, the reaction is felt on our shoulder. That is, the reaction is backwards when the bullet moves forwards. Similarly, here also when the torque is developed in the rotor, the stator realizes an opposite torque of equal magnitude. But what we are doing actually, the stator we fix it to the ground. When you fix it to the ground, the reaction of the stator is taken by the ground. We normally you find we use strong bolts. They are called foundation bolt. Foundation bolt. and at the end it will have some branched or split construction, so that the foundation bolt rigidly cemented to the ground, and it is able to withstand the torque. The higher the capacity of the motor and the stronger will be the foundation bolt. It is because the reaction torque should be absorbed, otherwise the stator will start rotating. So now here the reaction torque is to be accounted for by fixing strongly. But now what we do when we want to measure when we want to use the reaction torque itself to measure the torque developed in the rotor, then we don't fix the stator. That is the approach, logical approach. So that is here. Now it is a motor whose developed torque we want to measure. Torque T is developed. The torque we want to measure. So naturally, don't fix this stator to the ground. Mount it on trunnion bearings, one pair of ball bearings. Ball bearings of very precision and very small coefficient of friction. Such a bearing you could select and use them as a ball bearing. That is, now instead of fixing to the ground, and the stator is supported through a ball bearing and then fixed to the ground. So now it is not fixed to the ground. It is through the ball bearing it is fixed to the ground. So now when the rotor develops some torque, the stator will try to rotate in the opposite direction. Now since it is mounted on the ball bearings, it is free to rotate. But what we are doing is we support that at the free, and see here we have connected a lever from the stator body, and it is supported at the end by having a proper support, and we can measure the force F. To measure the force F, we can use any one of the transducers or to load cell, what you have learnt under force measurement. So when the reaction torque is there, the torque is realized as a force at a lever arm, so the torque is equal to F into L. By measuring the force at a distance of lever, that is what is shown here. The lever comes in front and support it at the end, and measuring the force we know the torque according to the relation, because L is fixed. So according to this relation we can measure the torque by measuring the force. So this is one method. The another method, now the second method, that is in case of small motors, say small motor of say few watts, so 10 watts capacity of such a small motor, weight will be few grams, say 100 150 grams. In such cases the reaction measurement is used can be used comfortably to find the torque developed in the motor. That is, now the whole motor is held in a holder by fixing two screws are there, fixing the two screws to the stator of the motor. This is hung, so from a stand. So this is a holder connecting the motor stator to the transducer, torque transducer here. It transduces the torque in terms of voltage. How it functions, one principle is we can explain here, that is a torque transducer, how the torque is converted in terms of voltage. For that we can use the microsyn. Microsyn we have learnt already in displacement measurement, and there it can measure plus or minus say 15 degrees rotations in terms of it can convert into voltage, proportionate voltage. There we have a rotor, material distributed against 4 poles, and each pole will be carrying excitation winding and also secondary winding. That principle we have learnt already. So microsyn changes the rotation of plus or minus 15 degrees into a plus or minus 5 degrees or 2.5 volts, plus or minus 2.5 volts. So angular rotation to the voltage is obtained by microsyn. Now the torque is applied. Now here as a part of the transducer, you will have 2 cylinders. It's a one cylinder, fixed cylinder, and and then a movable cylinder connected by so-called cross leaf springs. That is we learnt one of the pivot that also we have learnt spring pivots. That is in earlier bearings where the error source, to reduce the friction or to reduce the play in bearings, we have learnt the cross leaf bearings. It's one of the earlier lectures. So these 2 cylinders are connected by 2 cross leaf springs, middle spring being the twice the width of the 2 end bearings, 2 end springs. Springs are just flat spring steel material. So now if you can hold one cylinder and rotate the other cylinder proportionately, and that rotation is proportional to the torque. So if you apply more torque, it will also rotate more with reference to other cylinder. You can hold any one cylinder. So one of the cylinders will fix it, and the other cylinder the torque is applied. Now the torque is converted into angular rotation by this cross sleeve springs. So now this cylinder assembly, fixed cylinder, and which is fixed by means of 3 springs inside, convert the torque into theta. That is what is shown here, flexural pivot with the cylinders. Pivot is inside, so with the cylinders it is there. That assembly is converting torque to theta, and theta to E or voltage is obtained by having this microcyn mounted to the movable cylinder where we apply the torque. So when torque is applied, we get the voltage output. So such a transducer is made use of here, that we call it torque transducer. So the reaction torque is there on the motor. When the motor is under the torque, then naturally it is transduced by the torque transducer into voltage, which will be connected to an instrument. Yeah, that is the wire carrying the signal to the instrument. Now the different torques are developed in the rotating disc. Disc is fixed by a screw to the shaft of this motor. So by adjusting this gap, we apply different torque on the system. That is what we learnt earlier, eddy current dynamometer. This eddy current dynamometer, by moving this, by having different height of this plate, we can change the gap, and then torque is varied. Accordingly, the torque is realized by the instrument. And if we measure the RPM by having another pickup, we can plot the torque speed characteristics of the motor. So here essentially we are measuring the torque by having reaction principle. The rotor is developed. In the rotor, the torque is developed. The reaction is taken by the reaction torque available in the motor stator, that is being transduced by the that is taken up by the transducer and given voltage. Now when we are measuring the torque at the stator, does it include the friction torque? Because we know the rotor is mounted on the stator by 2 ball bearings like this. It is shown here. This is the rotor and this is the stator. There the stator is, or the rotor is mounted inside the rotor by having 2 ball bearings. So when we measure the torque at the stator, does it include the friction torque which is being dissipated as heat? That is the question. It is not the case. It is not the case. We measure only the transmitted torque. What is transmitted from the shaft, that alone is measured at the stator, not the internal friction. That is analyzed by this by the following analysis. Suppose TD, this rotation direction. So TD is the torque developed in the rotor. Then we know as a reaction, the reaction torque TR is developed in the stator in the opposite direction, that we know. Now what is developed torque? Developed torque made up of load torque. Here we have got load torque acting, and also acceleration of the whole mass, and the load mass also should be accelerated. So load torque plus acceleration torque plus friction. This also friction is there in the overcoming friction between the ball and race. So we find the TD, the torque developed, is equal to TL plus TA plus TF, that is equal to TR. TR is the equal amount. Whatever developed in the rotor, equal amount is developed on the stator immediately, that is reaction. Now what is the effect of friction? Friction is acting on the stator in such a way that is friction is coming through the ball bearings to the stator. In such a way, this is stationary member normally, it is being dragged to rotate in the rotation of the rotor. So the stator will be under the friction torque trying to rotate in this direction. So friction torque is in this direction. Now what is the net? TR is in this direction, TF is in this rotating direction. So what is TR is made up of? TR is made up of all the 3, and TF plus TF. This is minus TF, minus, because TF is opposite to TR, minus TF. Now TF DF gets cancelled, and what is transmitted is TL plus TA. That is what is available in the stator, that what you are measuring by having such a setup. So, when we measure the stator torque, we are measuring the torque transmitted from the shaft to the load and other things. So, that is what is important. Internal friction is not measured by the internal torque is not measured by this reaction principle. So, this is second method. First method is a transmission dynamometer. Second method reaction principle. Third method is strain gauge. This is C, method C, strain gauge torque meter. This is also widely used in shafts. So, this only in small motors. Bigger motor you have to mount in Trunnion bearings, but the error in Trunnion bearings, the error in such reaction measurement there using Trunnion bearings, the friction in the Trunnion bearings, friction torque is the error torque, error in measurements. So, when you select bearing for the Trunnion bearings, it should be having very low coefficient of friction. Such bearings we should take, and it is possible to keep the error within the limits. Now, the strain gauge torque meter, this is more precise and also widely used. Here what we are doing is this is a transmission. This is a shaft taking the torque from the power source to power sink. In between we fix these strain gauges. As I already told, in the force measurement, we have to weaken the place where the strain gauges are pasted, otherwise signal will not be sufficient. So, for that purpose probably you can make a flange joint, flange fixing, flange coupling, flange in between, and make a tubular member, that is where you want to fix the strain gauge, make a tubular member. The other thing may be solid. So, here we are fixing the strain gauges in a tubular member, so that we have sufficient signal for the instrumentation. Signal noise ratio will be sufficiently large. Now, we know in when there is pure torsion, that principal stress or strain, that will be given by sigma 1 or sigma 2, that is equal to sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 plus tau xy. This is when any element is subjected to two coordinate stresses sigma x, sigma y, and also a shear stress of tau xy, then this is square, tau xy square. So, and when there is shear stress, then principal stress will be given by this equation, and in torque applications we do not have these coordinate stresses. So, you find the principal sigma 1 sigma 2 is equal to sigma 1 sigma 2 is equal to tau xy, because square root of square. So, that alone remains, that is principal stress sigma 1 sigma 2 will be tau xy. The principal, that is same as shear stress will be appearing as the compressive or tensile stresses, and also the angle at which it will be oriented is given by tan 2 phi. Tan 2 phi is equal to 2 tau xy by xy minus sigma x minus sigma y. When this is 0, when sigma x sigma y is 0, now you find tan 2 phi is equal to infinity. So, 2 phi is equal to 90 degree and phi is equal to 45 degrees. So, at 45 degrees to the action of the direction of the shear stress, the principal stresses sigma 1 and sigma 2 or tensile compressive stress will be available. So, now it is this is the torque, this is the torque, we wrote this opposite direction. So, torque, it is twisted this way, that is torque is the shear stress in this direction. So, 45 degree to that is how you have to fix the strain gauges. So, if one is taking up the tensile strain, then 2 will be taking up the compressive strain. Similarly, opposite point, that is at 45 degrees you have to fix, that is how we get the direction 45 degrees. So, 1 and 3 will take tensile strain, and 2 and 4 will take compressive strain. So, in the shaft you have to mark a line, mark axial, and then 40 degree to that you have to paste 2 strain gauges 40 degree this way. Now you will find this both this is 90 degree, one axis to the other axis it's 90 degree, and it's called 90 degree rosettes are available in the market. 90 degree rosettes, strain gauge rosettes. In one mounting, the two strain gauges at 40 degrees or with the central line, it's also marked there. 40 degrees here, 40 degrees it's fixed, they are available in the market. So purchase one such things, and if we marking a line in the shaft and line on the rosette also coincide, we paste it with the cement as supplied by the manufacturer. Then similarly in the opposite point also, the diameter opposite point will fix these two strain gauges and connect them in the bridge network as per this diagram. So 1 and 3 will be taking up the tensile strain for one particular rotation at this, and 2 and 4 will be taking up the compressive strain. So when the torque is applied, then you will find you get a proportionate to output signal EO, and that can be calibrated in terms of torque. Now this instrumentation is sensitive only for torque, and it is not sensitive for axial or bending moment. That what we claim. How do you say this? Suppose it's being bent in this direction. Suppose it's being bent in this, a moment is applied in this direction, so it is bent. Then what will happen? All layers above the neutral axis will be under tension. So layers are 1 and 4. 1 and 4 are the strain gauges which will subject to tension. Now 1 and 4 in adjacent arms taking up similar strain, and it will nullify. It will not give rise to any output voltage. So similarly 2 and 3 will be under compressive strain, and adjacent arms it will not give rise to any output voltage. Hence the moment does not produce any, the bending moment doesn't produce any signal in the bridge network. Similarly, if it is compression, suppose you apply a compressive load, the whole shaft is compressed, will you get any error signal? No. It is because all the 4, when you compress the shaft like this, compressive force, all the 4 strain gauges are equally strained, and equal strain in all the 4 arms you already learned will not give rise to any signal in the bridge network. So this is the laws of the bridge. So you will find the instrumentation response only for the torque and the bending moment, and the bending moment as well as the compressive or tensile load on the shaft will not give rise to any error. Hence it is automatically foolproof for the other type of loading. So that is the rotating shafts. Rotating shaft torque, that is transmission type, can measure any one of these 3 methods. Now we go to the next torque measurement in stationary shaft. Now it is simple. Here it is a simple method. Here if you have got a shaft, the shaft is a fixed shaft, and when you want to apply when we apply a torque, then the layer AB twists to A B dash it twists. So if you want to measure this torque on the twisting, you can instead of fixing the shaft to the wall, you can as well fix to the transducer. So you fix it to the transducer. Now the shaft fixed to the transducer. So when you apply the torque, the transducer gives the signal. So it is easy method. Or you can also use the strain gauge torque measurement, fixing the shaft here and put your strain gauges 45 degrees. And now the wire can be little flexible wire, but previously now it is a rotating shaft, so you require these slip rings. 4 slip rings are required. These are the slip rings. 4 slip rings for the 4 corners, 2 corners for the supply, and the 2 slip rings for the taking output signal. So by using slip rings, we can take the signal inside and signal outside. If it is stationary shaft, such things are not required. So it is a easy method of measuring the fixed shaft by using the strain gauges. It is easier. As you have learnt force under force measurement, friction force, how to measure the friction force we have learnt under force measurement. Similarly, under a torque measurement, let us learn the friction torque measure, how the friction torque is measured. Friction torque is the common phenomena in all bearings. For example, you consider a sleeve bearing. This is sleeve bearing bush, or it is called sleeve, within which a journal shaft, journal is the shaft. shaft is rotating inside, and we have the lubricating oil. So as the shaft rotates in this direction, because of wedge formation, shaft is lifted. So when it is lifted, it is rotating, but due to viscous friction of the liquid lubricant, you find the sleeve also will be under the action of the friction torque. So torque will be there. So this is normally the sleeve is fixed to the wall. This is wall, where it is, yeah, wall is. So normally fixed to the wall. So the frictional torque is taken up, normally absorbed by the wall, since the sleeve is press fitted to the wall. So the phenomena here is, due to the friction torque, the sleeve will try to rotate along the shaft, but it is not allowed since it is press fitted. But when we want to measure that friction torque, naturally do not fix it to the frame and mount it, as you have learnt in the reaction principle, you know. Here we mount the sleeve on 2 ball bearings, you can call it Trunnion ball bearings, 2 ball bearings, so that now the sleeve is allowed to rotate in the same direction of the journal. This is the journal, this is shaft or journal. The portion of the shaft inside the bearing is called journal, that is all. So there will be gap, but due to here I have exaggerated clearance, but normally the gap will be of the order of d by 1000. This is the diameter clearance in any bearings. If d is the diameter of the journal, then the clearance will be d by 1000. If 10 mm shaft means 10 microns will be the clearance inside a bearing. So within which the oil is there, it will create the wedge formation, and hence the relative motion is allowed there. Now due to this rotation, the suppose it is rotating in this direction, yeah, it is direction is shown here. So the sleeve also will be trying to rotate, but it is not allowed to rotate by having, suppose I take the cross section here, one lever is fixed to the sleeve, it is fixed to the sleeve, that is bush. So when the bush tries to rotate, it is not allowed to rotate by supporting it at a distance, L. And you can use any force measuring technique, that is any load cell, so that what is the force due to this torque at this leverage L. So if F is the force, F into L will give the friction torque in the sleeve. That is how we use this method of fixing a lever and measuring at the distance to measure the friction torque on the sleeve bearing. There is one method. Here the error is the Trunnion bearings, whatever we have got the error, whatever we have the friction in these ball bearings, that will be the error in the measurement. But we know that in ball bearings the friction coefficient is very small compared to this is sliding bearing, sliding bush type or sleeve type bearings are called sliding bearings, their friction will be much larger. So that friction torque is larger one. So if we that will be smaller portion of, ball bearings friction will be much smaller, hence it is allowable error. Normally it is under allowable error limit, that is error source. And another better method than this method is called pendulum dynamometer. For small bearings less than 10 mm inside diameter bearings you can use it, whereas the other technique you can use any bearing, any size. So small bearing. So this is the bearing. Bearing sleeve, you can call it bearing sleeve, and this is holder. This is the pendulum. This is the weight of the pendulum. Pendulum is fixed to the holder bottom. So what happens when this is support bearings? So the shaft is rotated by, you will have the motor and all fixed here. So it will be rotated, and due to that rotation, the sleeve also will try to rotate along the shaft due to friction torque. So when the sleeve try to rotate, suppose this is rotating speed, so that I will hatch it, and this is the sleeve is this direction, this is the bearing bush or bearing sleeve. Bearing sleeve is mounted in the bearing holder. So this is the bearing holder, at the bearing holder bottom we have fixed the pendulum. So suppose this is direction of the journal, so the sleeve also will try to rotate, and when it rotates, the weight which is at the bottom is moved by a distance x. The moment it has moved, it applies a restoring torque. So you find the friction torque trying to rotate the pendulum in this direction, whereas the weight is trying to bring it to the original position. When both of them match, it will stand there. So you will find this is a measure of the friction torque. So W into X is the moment restoring, and the deflecting torque W mu into R. R is the radius of the journal. R is the radius of the journal. So mu is the coefficient of friction between the journal and the bearing, and mu W into mu friction force into R will give you the friction torque. So friction torque is equal to W into X. So that is W into X is equal to this under equilibrium condition. We just under the equilibrium condition measure this X from the neutral position how much it has deflected. So from that mu is equal to coefficient of friction between the journal and the bearing bush is X by R. That is how the friction torque and the friction coefficient of friction is found out. Here the error is no, more or less is not there, except the measurement technique may have some error in this measurement of length. This is second method. Third method is coast down analysis. This is mainly used in electrical motors. What is the friction torque in the electrical motor? So the technique is you switch off the power supply to the electric motor. Now the electric motor decelerates. Now the what is the speciality of torque? How the torque and force are analogous to each other. If force when you apply on a body, the body moves on a linear line with an acceleration a. Similarly, when if you have got a mass on a shaft and it is pivoted, and now you apply a torque, J is the M is the mass here. So F is equal to M into A. F is equal to M into A for linear. When you apply a force on a mass, that mass accelerates through A along linear axis, whereas linear direction. Whereas torque when you apply on a body like this with a polar moment of inertia J, then it accelerates in an angular direction. That is all. Force and torque imparts acceleration. F acts acceleration along the linear direction. Torque gives acceleration in the rotary directions. With the equation T is equal to J into A. J into T is equal to J into angular acceleration alpha. So you can use torque to accelerate or decelerate also. That is what is made use of here coast down analysis. Whatever available the friction torque, once you cut this power supply to the motor, that the rotor decelerates. That deceleration is proportional to the friction torque. That is the principle. Assuming that there is no windage loss in the motor, it's only friction torque which is causing the deceleration, then you will find deceleration. We find it. We plot the variation of the RPM of the motor with reference to time. That you can, by giving a tacho generator, that voltage is, you can plot it in a slip chart recorder. So you for a few seconds let the deceleration that the RPM be plotted, and from that you can find out the acceleration or deceleration. Deceleration is negative of the reducing acceleration is called deceleration. So if dn is the RPM difference for a duration of dt, so probably 100 RPM difference for a 5 seconds. So 100 by 5 you put it here. So that is that is RPM. You convert it into second by 60. Then RPS. Then 2 pi you multiply, you got the radian per second square. Then you will find that friction torque is equal to J, the rotor moment, rotor polar moment inertia is given by manufacturer J, then multiplied by the deceleration will give you the friction torque TF. So that is how we arrive at the friction torque in an electric motor, that by coast down analysis, allowing the after cutting the power supply, allow it to decelerate, and that RPM is plotted. From that we can find out what is the friction torque in the bearings. Yeah. It is very important for a mechanical engineer to design the tubular member for when you want to measure the torque in any transmitting shaft. So as I already mentioned for the strain gauge torque meter, that where we want to paste the strain gauge, it should be made tubular structure so that we have sufficient strain there. Secondly, tubular member will have large area so that we can easily fix the strain gauge. If you go for solid shaft, then it will be very small diameter to produce sufficient strain, and in the small shaft you cannot paste the strain gauge. That is the problem. To avoid it, we go for the tubular member. It will be weak, at the same time we have got sufficient area. So to illustrate that, we have worked out one problem here. That is, this is actually an industrial problem. the torque transmitted by a steering wheel of a vehicle, of a car, is to be measured, and maximum torque in that steering wheel in a very rough road condition is around 70 Newton meter. Suggest suitable thickness for the tubular member made up of mild steel for fixing strain gauges with outside the tubular member outside diameter being 50 mm. This member is fixed as part of the axle, then only the whole torque will go through the strain gauge through the instrumentation. So it is part of the steering wheel, and toe allowable, that is maximum shear stress in this mild steel is 12 into 10 to the power 7 Pascal, and the Young's modulus of steel is 2 into 10 to the power 11 Pascal. At the maximum torque there should be 200 microstrain, that we know, because the strain gauges we paste, it measures principal stress, tension as well as compression, and that strain should be around 200 micron, that we normally adopt for instrumentation. Same thing we did for force measurement also, workload problems. So now the solution is, to produce 200 microstrain, necessary stress should be 40 megapascal, that should be the principal stress, and to produce that principal stress we know the other rectangular component is 0, the toe xy, that is the shear stress should be of the same principal stress. So toe is also of the same order, so that is a shear stress of this much produce a equal principal stress, which we have seen previously the equation. So the corresponding to principals of 40 megapascal, shear stress should be 40 megapascal same, since toe is equal to sigma, sigma is principal stress. Now the problem it is given, toe maximum, toe allowable is 12 into 10 to the power 7, and here we have got that is 120 megapascal. Here we have only 40 megapascal. So toe is less than toe allowable, that means we can go for 200 microstrain. So that you have checked. Now we go for the equation for the torque, T by J, polar moment of inertia, is equal to the shear stress by radius or the outer surface, or whatever it is, the radius. At particular radius, what is the shear stress? This is the equation well known. So T here is T maximum is 70 Newton meter, and J is the polar moment inertia of the cross section area, and the shear stress is 40 megapascal. So the radius, that is outside diameter, is given as 50 millimeter is given. So that gives rise to a radius of 25 millimeter, that is in terms of meter 10 to the power minus 3, gives rise to a J of 43.75 into 10 to the power 3 millimeter to the power 4. That is the polar moment of inertia. That is the area. Yeah. So the annular area should be of this, should give rise to a polar moment of inertia of so much. If that is the case, then if the J is polar moment of inertia in terms of DO, and this is DI, and outside is DO. So if the DI, DO are the inside and outside diameters, then polar moment of inertia is given by this equation. So DO is given as already 50 mm. So DI from this equation you get 49.08. You can say take it as 49 millimeter. So thickness for outside 50 and inside is 49 divided by 2, 0.5 mm. So that should be the thickness of the tube. Then only you will have sufficient stress and sufficient strain. Our instrumentation will be sufficient sensitivity, so that we can measure the full range of the torque up to 70 Newton meter. So that is how we have to design the primary transducer, transducing the torque to strain. Yeah.